Welcome to Bio-IT World's Trends from the Trenches podcast, your insider's look at the science, technology, and executive trends driving the life sciences. I'm Allison Proffitt, editor of Bio-IT World. In this special episode of the Trends from the Trenches podcast, we bring you part of the Trends from the Trenches session held each year at the Bio-IT World Conference and Expo. Earlier this month, Ari Berman, CEO of BioTeam, shared on-the-ground insights from BioTeam's life sciences IT consulting business. Let's listen in.
Let's get started. So hello, everybody. Thank you for staying till the last session of the conference. And thanks for filing into the abbreviated Trenches room this year, and excited to talk to you. Today, there's two of us from BioTeam talking, delivering trends. It's myself and Laura Okolebo, and we have 90 minutes and 90 slides, so that should be fascinating. In traditional trends from the trenches history. So for those that don't know, this is a talk that this will be its I think 12th year now that we've done it. And so I can't talk as fast as Chris Dagg, but I will come close. So here we go. All right, so this is the only plug I'm going to make. So you are here for true, industry knowledge and stuff. But for those of you who have no idea who we are a company called BioTeam. We're a consulting company of deep experts. We really try to bring science and technology together in a way to really drive science forward and make science go faster. We're booth 404, which is actually not found. You can go find it, and that's where we are. Okay, so what to expect from this talk? Chris Dagg, one of our founders, has given this talk for 10 years. He retired from doing it last year. He was literally like, I can't do it again. All right, and he's like, I love it, but I can't do it. He's an extreme introvert. I'm more on the extrovert side. So I made the attempt, along with a few others, to take it over from him last year. So the focus has really always been on, blunt, really honest, practical lessons that we learn out there, because as BioTeam, we're out there with a whole lot of organizations. And we get to see how a lot of different people, some smart and some people who are maybe a bit confused, try to do things, and we get to really assemble that from the whole market. So and because we don't resell anything, we can generally speak in public pretty bluntly about things and just call things out when we want to. So the idea is really very little filter. I have slightly more filter than Doug, but no marketing type of stuff. So who the heck are we? Laura Okolebo down here is a scientist, a senior TED fellow, and a senior consultant at BioTeam. She's that sums you up, I think, right? Passionate about equality and empowerment in science and solving really hard problems. And she's going to sort of talk about the practical applications of what I go through, trends in the field. And I'm Ari. I'm BioTeam CEO. I'm a scientist, technologist. I've been with BioTeam for 12 years. And the goal is to be informative and hopefully entertaining. And so I'll do trends. Laura will talk about when trends fail and what to do about that after that. So this is something I stole from Dag's talks here, the thought excreter magic quadrant, just sort of saying that, look, the reason we're up here isn't because we're necessarily the world's experts in these things. It's because we can talk pretty honestly and bluntly about things. And so that's what we're going to do, because neither of us have a problem being blunt. All right. So I'm going to start with sort of an overview, grand challenges sort of things. All right. So, we, I think as an industry, if you break it down, have three major grand challenges. Okay. And the current state of those are, I'm just going to go from, left to right here. IT support for science is inconsistent and not aligned with science. I think I've been talking about that for a couple of decades. Next, and so you'll see the one on the left is IT infrastructure, the one in the middle is data, and the one on the right is kind of people, all right? And so in the middle, a fractured data ecosystem. We have a hugely fractured data ecosystem and minimal standards, or at least minimal unified standards, and fair. And advanced analytics tend to be built by people, by data scientists who are experts for experts. All right, so those are some of the problems. The effect on science infrastructure is a barrier and not an asset, scientists end up doing it themselves, right? There's a lot of shadow IT. There's a lot of figuring it out themselves. There's an enormous productivity sink just getting data ready for analysis. It's at least 80% of the time that people spend on that. Imagine how much productivity is lost there. And data scientists end up becoming a bottleneck for the long tail of science, right? Lab scientists really can't do the analysis on their own because it's not designed for them to do it. So here are the grand challenges. We should, as an industry, create advanced infrastructure for science that's abstracted from the users so that it works, they know it works, they don't care where it's running, it just does, right? Which also would help IT support it better. And so that's a unity in the middle that's actually shockingly hard to do. This is possibly even harder to do. We should unify the biomedical data ecosystem. Think we could do that? Yeah. All right. This I know we can do. We just have to put effort into it. Let's make advanced analytics accessible to the long tail of science, right? And so if we do all that, science goes faster, and that's why we are here. All right. So with that background, let's jump into trends. AI. Thank you. We're done. Have a great day. That's all we need to do. That's what we're doing here. Obviously, I'm kidding, but more on AI later and all that. But getting more into it. So I'm going to put some big picture in here. So why are we all here? So scientific discovery drives modern medicine, all right? A really interesting way to measure scientific progress is human lifespan. And so if you look at this graph on the right, it shows the progression of human lifespan from 1770 until 2019, or sorry, 2020. And you'll notice that, at least in the US, we hit a maximum lifespan in the US of 76.7 years in 2019. It dropped after that thanks to the pandemic. All right. And if you look back at 1865, things were pretty flat before then. Right. Before 1865, the average human lifespan was 35 years. Can you imagine that? 35 years. And before that, that's essentially our natural lifespan. But germ theory, and using antiseptics in surgery, learning how to wash our hands doubled human lifespan. That alone. Right. Very, very quickly. After that, vaccinations, epidemiology, anesthesia, antibiotics, and others, those things kept it on a steady pace upwards. All of this is driven by basic life sciences research and applied to human health. But the issue now is that this long lifespan and the idea of health span are sort of out of sync. Health span is the percentage of life that one is considered healthy, right? There's a lot of definitions of what healthy is. And so for the sake of this discussion, let's just say that the average age of health decline is about 63 years old in the US versus a 76.7-year lifespan. These are all these age-related diseases that make life a lot more difficult or end early. And so what we really do is live about 20% of our lives unhealthy overall. So we got a long lifespan, but the last 20% of it kind of sucks, right? This has resulted in all sorts of issues, soaring healthcare costs, increased burden on medical and economic systems, and our population ages poorly. So we argue that medical science needs a new focus. Historically, medicine and the outcomes of medicine have really focused on reducing the risk of death, okay? Yeah, sure, let's not die. I'm good with that. But medical science has really advanced to the point where that focus isn't as relevant. We need new breakthroughs and a focus on living healthy for longer, right? Which is probably going to also help us actually live longer. Modern diagnostic computational methods have already started moving towards this reality, which is that's driven us as a society trying to move towards precision medicine. Okay, so this is sort of, let's move away from the one-size-fits-all thing of medicine, the sledgehammer approach to human health, as I call it, where the TV ads have to spend 28 minutes listing out the side effects because it wasn't designed for everybody, right? And so instead, let's deliver care that's unique to the person. Right? We sort of have the technology right now, but it's really hard to do, and critically, no one really knows how to make money from it yet. If we can figure out how to make money from precision medicine, it'll go. But the real goal of precision medicine is increased health span, right? Specific medicine that helps you be healthy for longer, especially since we're more than double outliving our natural lifespan. There's some foundational data initiatives like All of Us, Candid, TCGA, InsideRx, and there's a whole bunch more that I'm not naming here that really are trying to make this work. And ultimately involves a huge amount of data collection and modeling and classification to pull it off. So Getting into things. So infrastructure in life sciences and healthcare. This is historically where this talk has focused. I go through quite a bit of the infrastructure bit here, and then move on to some other things that we also focus on now. So let's start with basic data generation, all right? We are at an all-time high. That shouldn't surprise anyone, but we've collected an estimated of 120 zettabytes of total data to date. Does everyone know what a zettabyte is? Raise your hand. No? Okay. A zettabyte is 1,000 exabytes, which is 1,000 petabytes, which is 1,000 terabytes. Okay? So it is a lot of data. In 1995, we didn't have enough raw materials on planet Earth to store 1 zettabyte. Okay, but we have our compression algorithms and our technology has improved, so now we can do that. What that means, interestingly, is that last year alone, we collected 23 zettabytes of data. That's a lot. That's a lot of data. And so that's a massively exponential, almost straight up curve. That's 10 gigabytes per person on planet Earth per day. All right. So if we reduce that to our space, laboratory and health diagnostics, the rate of generation in life sciences is huge, right? Way outpaces Moore's law. This is a real famous graph from NHGRI showing the cost of generating human genome and graphed against Moore's law. It's, $500 to $1,000 or so to generate a genome today, and that's amazing and also ridiculous, considering it was, 12 years and $13 billion to do the first one, right, 15 years ago. So it's come a really, really long way. So laboratory technology is really innovating on the order of about a year or less. There's new stuff coming out, new ways of doing things, new ways of analyzing things. HPC and IT and the ability to do those computing things really are on the order of many years. And so, equipment life cycles are 3 to 6 years long. And so how do you match those innovations up? The truth is most of us don't, right? And so cloud has really enabled a lot more rapid cycling, but it tends to be more expensive and more complex. And, health diagnostics, sensor data, trying to make sense of clinical trials in more modern ways, it pushes that amount of data and the complexity much higher. So I don't know if everyone knows this, but life sciences and healthcare is among the highest, the top data generators of all the sciences, right? This is in comparison to astronomy and high energy physics. We're talking like, the Large Hadron Collider, for instance, has this Atlas 2 detector, collects 6 petabytes of data per second. Okay, we're outpacing that just through pure parallelism. We have single labs that can generate a petabyte of data a year, right? And so we've got 85,000 labs in the U.S. So most labs have equipment, things like these lovely things on the right there, that can generate tens of terabytes per week, and that kind of data takes a lot of sophistication to work through and a lot of computational power to work through. And so, bioinformatics and data science has sort of taken over that analytic space, and AI. There's the word again. Computational sophistication is really required to be able to compete. And clinical informatics is really, finally shoving through that barrier and becoming a major health diagnostics tool. So what does this mean? This means that high performance computing is a laboratory tool. Okay? It is not an enterprise IT service. They can be the same thing, but ultimately it's a laboratory tool. This is something that you must have in order to compete, in order to discover, in order to actually process modern data-intensive science. And so if you take nothing more away from that, take that. So, all right, getting into trends. And I forgot to make this change. So some nomenclature. I'm doing something a little different this year. So for each trend, I'm going to show a stoplight showing its effect on science. The one on the left, and these will always be in the same order, for those of you who, I'm sorry, can't see red and green, means that red means it's more challenging or a negative trend, and it's making science harder. All right. Yellow means it's a sustaining trend. It's keeping science moving as it is now. It's not inhibiting, but it's also not really helping it move forward faster. And green means it's an innovating trend and it's helping science go faster. And so again, left to right. On that. And it'll always be up there in every slide. All right. So let's talk about infrastructure for biomedical research. Trend, computing's hard again, and this is bad, all right, in a lot of ways. So the red light's on there. HPC infrastructure and services landscape has really started to diverge away from what we thought was a figured out landscape a few years ago, just in 2019. We've got this sort of redifferentiation of services happening. For a while, they're just, you can do like one of 4 things to really compute. Now there's hundreds of things. All these services, clouds, you can put stuff on premises. You can do, all these different services. And so there's just way more options and a lot more specializations in hardware to use compute and services with. And so, there's just not a lot of uniformity to the platforms anymore. And this is both bad and sustaining. The pandemic kind of changed the game. Everyone went home into isolation, labs shut down, and researchers were like, oh, wait, what do I do with my time now? Oh, I've got data to analyze. Let me start analyzing the data, all right? And so what happened was everyone tried to start getting into their HPC systems or their cloud systems and ramped up their usage a lot. And that users normally wouldn't use it were now clamoring for time on their systems. I think everyone's VPNs got like swamped because they're made for 10% of the population, not 100%. And what that really did is it made on-premises infrastructure become really hard to manage remotely. We didn't know how to do it. I already said the VPN bit. And it wasn't prepared. No one was prepared for remote science. And local IT could barely maintain the status quo through that. The other thing, which was very bad, and is still bad, is that infrastructure got scarce. It's genuinely harder to get hardware now. It's easier than it was a year ago, but it's still really hard. There's global supply chain issues still. There's the explosion of AI. There's that word again. We should have a drinking game for every time AI is mentioned. And everything is more expensive. Inflation is a real thing. Ran into a client, spent $100,000 on an H100 GPU for one. All right? This is crazy. Did anyone see Dan Stanzione's talk on Monday? He said he would rather load the racks with gold bars than these things because it would be less expensive, right? And so, but the other thing that's happened, which is interesting, is that there's been a change in investment priorities from organizations in the pandemic. Everyone's paying for buildings that aren't being used, right? That's a massive cost, and there's good reasons why people aren't using them. And so we're sort of in this weird in-between time of there's a lot of cost going somewhere that's not being used. And so organizations generally are questioning capital expenditures. Do we want to invest in something or not? Scientists sort of got started on these deep analytics when the labs closed, so the demand is up at the same time. And at the same time, we're in a declining market in our space, right? Our government really couldn't figure out how to fund itself, until 2.5 weeks ago. As a result, it set off a series of downward spirals. Grants and new investments were really delayed with NIH in particular. Contractors weren't getting enough work. Every major organization that I know of is laying people off. Pharma's downsizing from an inflated and stressed drug market. There's underutilized office space and properties, as I said earlier, and drug pipelines are slower, and early development is sluggish, and approvals are slower, and innovation is slower because of all the stuff we just went through before, right? Just sort of this feed-forward cycle. And so, at the same time, 2001 to 2023, and maybe even now, venture capital and private equity kind of dried up in the life sciences space. It was hard to get that. There's a lot of people running around trying to fund it now, but we were in a biotech winter, and so that has decreased investment. But there's suddenly a resurgence of on-premises HPC planning. And this is good, right? Because that shows promise that things might start to move again. Without the right computational infrastructure and the right support for it, these innovations just aren't going to happen now. And I think that those things are very linked. All right, so let's get into some specifics. CPUs. Processors, all right? This is I'd say it's innovating. Intel isn't the only game in town anymore, and frankly, they're starting to lose their foothold in the HPC space in some ways. Choice is always good. A while ago, Intel was the only thing that mattered. Intel has the Sapphire Rapids Xeon scalable processors now. They have about 60 compute cores, 120 threads for those that use those, and next generation PCI, which allows really fast data transfer and other things. AMD surged onto the field a couple of years ago, back onto the field a couple of years ago with the Milan and now upcoming Genoa CPUs, and they have 96 cores to them, each socket, right, and 192 threads, and so that's really big. And now ARM, the Neoverse 3, which is being farmed out to a whole bunch of folks like Fujitsu, up to 128 cores per chip. Right, the NVIDIA DGXs have this in the center, one of them to run all the other chips in there. So the fourth fastest supercomputer in the world, Fugaku, which was the fastest for a while, is actually made of ARM processor. Fujitsu A64FXs, it had 7.6 million cores on that system, still does, right? Sits out on the ocean in Osaka, it's kind of interesting. And it was half an exaflop flops, floating point operations per second, all right? And that's traditionally how computer speed is measured. The moral of the story is that you can get ultra high density compute. We're talking 150 kilowatts a rack. That's insane. That is one rack, one thing about this wide and, taller than me, sucking up 150 kilowatts of power. You can get, with say, AMDs, you can get 768 cores per quad chassis. This big, 4 servers in it, right? And that means that you can get 11,000 compute cores in a single rack, a 56-unit rack, right? About a 7-foot tall rack. So that's insane. The first cluster that I built in 1994 had 128 processors, period, and it took up half a room, right? So this is a real thing. And so the cool thing about this is that high-density compute, as long as you can power it, means potentially high-density discovery. So there's a lot of potential. You can do more with less. Okay, GPUs. I'm labeling this one red. There is a literally insane demand for GPUs, and then when I say insane, like people are just crazy, right? Largely from NVIDIA. I already said this. People are paying $1,000 for a single H100, and the gold bars comment we just said. AI-crazed fever pitch has led to this trend, right? Not because it's what everyone should be doing, it's because that's what everyone thinks. And so this is the reality check. GPUs are not magic. They make 30% of all scientific workflows go faster. Not 100%, 30%, right? Deep learning is one of them, and the rest cannot use them. Right? They are not processors. They are not CPUs. They are highly parallel vector processors made for graphics that you can use if your algorithms can be ported over to vector processing. All right? And so if you can, it definitely makes it faster and it's definitely worth it, but it's not it. Everyone I talk to now is only trying to buy more GPUs. Only. Period. I'm like, what about CPUs? Oh, we don't need those. Yes, you do, because if you don't plan for those, you're leaving 70% of your analytics out of the game. So think about both, all right? That's why it was red. However, the GPUs themselves, I think they're sort of in a sustaining environment. Mostly it's sustaining because they are hard to get, especially the NVIDIA GPUs. The H100s, the Hoppers, they're very fast. They're super hot. I mean, you can heat your whole house with one, and they're very expensive, right? They're selling for, $40,000 to $100,000 right now. They're a little bit lower power than others, about 350 watts, and a high bandwidth memory access on them is very interesting for really high performance things. A100s and V100s, the two prior ones still work great. So if you got those, keep them. They work fine. And the NVIDIA GGX SuperPods are sort of the marketing goal of NVIDIA. Buy a whole bunch of our boxes that run this, that run the Mellanox backend that we also bought. And those things are sort of the AI supercomputer thing. So that's interesting. AMD Instinct MI300Xs, those are really interesting. They are the competition for H100s. They're much more available, and they are potentially faster in both data retrieval speeds and its storage capacity, and they outperform the H100. They are much cheaper, like 10 to 15K, but also higher power. And also, if you use GPUs, the only way to really use the NVIDIA GPUs for analytics is to use the CUDA libraries, which NVIDIA created to sell its chips, but also to make it useful. We couldn't do any of this. AMD doesn't have that, okay? They're not CUDA compatible. So you have to use the ROCm libraries, although very recently AMD came out with Z-Luda, which looks really promising, which will translate CUDA code to theirs. And so we'll see how that goes. Intel tried. They're trying. I'm sorry if there's Intel folks in here. But they've been trying to get into the GPU space with their Max 1550. It's interesting. It's a bit harder to use than the other because they don't have the software platforms, and they're really slow in production. But they have possible useful performance advantages in simulations. Okay. The point is that we need a balanced approach. We need balance. You have to balance cost, usability for science, and performance, right? Most of life sciences is not like, I got to go as fast as possible. All right. Most people are like, can I do it at all? All right. And so you may not need to push this all the way off the cliff because, it's shiny and fast and cool. So you might want to balance this out a little bit. There's a ton of other coprocessors out there, not just GPUs. All right. This is sort of in a sustaining space, I would say. Has anyone heard of Cerebrus? Wafer scale AI? Yes. And so That's that thing up there. It is literally an entire wafer about this big, a single chip. All right, and the giant box that guy's standing next to is what houses one, right? Just to cool the thing, all right? And so they've got all sorts of tensor cores on that, I think 1 million cores or something. It's, the entry point is like $5 million. And so you've got to really want it. The clouds have all jumped into the space with their own coprocessors, AWS Inferentia, Google TPUs, et cetera. I didn't list them all, but and then services like SageMaker and some others. And then there's some really interesting other coprocessors that are new to the market. Voltron Data and Next Silicon accelerators. Those are really interesting. I couldn't find any pictures because they're so brand new. But they're really thinking differently about how to process high-intensity algorithms by using a combination of programmable arrays and traditional CPUs in ways that just work without you having to do much. This is sort of a group coming out of Stealth Spinnaker with a Spinnaker product from SpinCloud. That's a picture of it connected up to some Raspberry Pis on the bottom there. And they're building this crazy flexible hardware architecture that can approximate quantum, they say. So I don't know what that means. But it's really designed to work more like the human brain. And, for the 15th year, FPGAs are still a thing. So, all right, so transfer HPC, interconnect, and networking. This got harder, actually. So connecting your boxes together to make the supercomputer go, that got harder because NVIDIA bought Mellanox. And so InfiniBand is now an NVIDIA thing. It got more expensive, but it's less expensive if you buy their superpods because it comes as a package deal, right? They're still one of the best on the market, Mellanox, but it is, again, harder to get. Everyone remember OmniPath? InfiniBand-like, pulled in some of the Cray innovations. Intel was running that. They divested it into Cornelis Networks, and it's still a thing that may resurge due to the NVIDIA thing. However, Rockport Networks is sort of interesting as a RDMA over converged Ethernet solution. So there's scaling issues with it. But the reality is that Ethernet is so fast right now that you probably could just use Ethernet. You're not going to run into latency issues. And so that's interesting. Another thing which I'll talk about on the next slide is composable architectures, right? Composable infrastructure is something that could change how we're designing HPC. It's much more cloud-like in how it's put together, actually, in a lot of ways. And just to do a shout-out real quick to MemVerge. This is super interesting. I don't know if you've talked to them. They're out of California, and they do a bunch of things, but one of the things that they do is universal checkpointing. Does everyone know what checkpointing is? If not, I'll describe it. This is like if your job crashes, you can start it up again, and it'll pick up where it was. Right? And that is really hard to do for scientists writing in Python who don't understand that you can dump the memory core out and then reload it. This does it automatically. And so that's pretty cool. Universal checkpointing may actually be a thing now. All right, composable infrastructure. What does this mean? This means that you can create a virtual node of hardware out of a whole couple of racks of nodes, and it'll work like it's an actual machine that you built that way. This is really interesting. It uses PCIe switching, so it really does connect the motherboards on a level together that it works pretty closely. There is a distance limitation of I think about 7 racks until that starts to break down, but you can get some pretty massive nodes in here. You need a node with 32 GPUs. Because I don't know why, then you can build one with that, right? If you're doing those sorts of things, and so it reduces the need for exotic, heterogeneous HPC designs. For the entirety of for the 30 years that I've been designing HPC, we always had to have several different kinds of nodes to accommodate different types of workflows in our space. Huge memory nodes, sort of the big standard ones that do everything. Certain ones that were bound together differently for the tightly coupled workflows. GigaIO and Liquid, they're the major players. There are about 5 others that are working on this. And there's an open standard that's being worked on called CXL that is sort of composability built into the processor set. They'll still work. And so this is interesting if you're interested in looking at that. All right, storage. Composability, I had, it's still early days, so it's sustaining innovation, but it's also possibly an innovation. So I have it green as well. All right, storage. I could give the entire talk on storage. I reduced it to one slide. So just for you. The reality is that it's freaking hard, all right? Storage has always been hard. It's always been sort of the bane of most of our existence. How do you store all this data? Still, most of the vendors will still try to sell you how fast they are. The reality is that the very smallest amount of storage you have on an HPC is what you need to go fast. The vast majority, you just need it to work and store and save stuff, right? And so most organizations really go over for volume and cost over pure performance. And so, don't fall for really the speeds and feeds like we're so fast and all this, except for your 1 petabyte of scratch storage you have on your HPC. That's worthwhile. So cost, space, and power is always a limiting factor. With solid state disks, they're no longer as heavy. They're also not as hot. A rack of disks used to be able to make sure that it wouldn't fall through the floor on in your data centers, and so because it's super, super heavy. And I'm going to talk a little bit about this later. We basically have to plan for infinite storage in our environments, right? Because no one throws anything away. And I'll talk about this a little bit later, but we don't really have good data lifecycle management for scientific data. We have to keep it all. NIH says, they don't actually say so. They say some of it and parts of it, but everyone's like, nope, it's everything, right? Because it's easier. And so, there's some really interesting, it's saving things in the cloud. It can get real expensive at anything above a petabyte for sure, but it can get really expensive too, unless you use one of their, 12,000 tiers of storage that you have to manage and figure out, right? And so, there's some interesting things in data management. I'm just listing one here real quick. Hammerspace, they're really interesting. I don't know, does everyone remember Avir from way back? Microsoft bought them. They were really, they were sort of a universal global buffer that made your storage faster. People were putting it in front of Isilon arrays, to speed up data in and out of them because the Isilon arrays were cheaper if they were slower. This is way more of a unified data management system. It's expensive, but it's interesting. So, and there's a few others like that. So like Globus, for instance, is doing a lot of this now too. Their subscription fees are lower, but they're also real big into high performance data transfer. Okay, so the most common on-premises storage for HPC is still GPFS, still. Right? So IBM still has some sort of a hold on this. We still run into that the most. I don't see Lustre very often in life sciences space. I see it in giant supercomputing centers. But Lustre was not good for a long time. And DDN pretty much owns Lustre now because it doesn't handle tons of small files well. All right? It's just the way the architecture is. DDN's been promising to improve that this year. We'll see. Next generation storage systems that are largely software defined storage are really interesting. They're both very present here at this Vast and WEC are sort of the main players. I think Pure is here too, and they're making an impact. We see a lot of this, a ton of this going in lots of places, and so it's an interesting way to go. And it's not more expensive than GPFS or anything like that, and it's definitely faster. And they have hybridization to clouds, which is also very interesting. Power. Okay, so who's thinking about power in their data centers? No one? Probably. And so if you saw Dan's talk the other day, he mentioned that we are really heading towards a power availability cliff in our space. And so this is really bad. There's a prediction that in the AI industry, by 2027, as a whole, will consume 85 to 134 terawatts of power a year. That's enough to power the Netherlands for a year. All right, that's insane, and it's just not sustainable. It's too power intensive. Not to mention heat production and actual global warming, literally warming the globe with our AI processing, right? So, and we were worried about this, and still are worried about it with cryptocurrency and blockchain and things like that, because that's a whole other thing. All right, so we need other methods for cooling or power efficiency. I don't know if anyone went to supercomputing last year or the year before, but it was basically all cooling, everything. There was immersion cooling, there was direct liquid cooling. There are ways to get your power to energy utilization rate like way up, and that's one way to do it, and also to keep things a lot cooler. And also keep using CPUs. They're a lot cooler than GPUs, and not everything uses GPUs. All right, so I've got just about a few slides left here. So I'm going to run a little faster because I'm running long. Okay, so trends in cloud. All right, who uses cloud? Everyone, come on. All right, I'm gonna bash it a little bit. So when the pandemic happened, they launched a brilliant marketing campaign saying, yep, you can't get to your stuff, you don't have enough stuff, come use the cloud. And they convinced decision makers to really go to the cloud. And one of the problems with humanity is that people tend to think in absolutes, all right? A solution can only be this or that. If cloud, then all cloud. Let's abandon things that work well because this will be better. Reasons, everyone's doing it. It's cool, so people will invest in it and support it, and leadership likes to talk about it. Sorry, I forgot to take that bit out. That's out of the talk. The reality is that this is a super nuanced situation, right? There are no absolutes ever, anywhere, and it isn't simple. Even turning on and off a light switch is not absolute, right? You can stick it in the middle and it'll spark, right? Think about that. So what happened as a result is that there were aggressive cloud migration programs. Most science organizations basically weren't planning for anything on premises. They were saying, let's go to cloud, let's transition away from local architecture. And cloud providers really were and still are very much incentivizing this, giving deep discounts, a lot of direct support during the planning and migration to cloud. And again, there are good reasons to do this. So stop planning on local stuff at all. And we've seen this movie before at BioTeam. So quick look back to the last wave of cloud migrations when AWS was somewhat newer. In 2008 to 2014, we helped several organizations migrate to the cloud and close their data centers. The only one out there was AWS. It was a whole lot less sophisticated than it is now. But the draw was that it was cheap, easier to manage. There's an endless supply of compute power, less staff, and all these things. And so, it was better shared access for external collaborations. These things are true, right? Better access to public data sets. The reality is that it was 10 to 50x the actual operating cost of data centers. Clouds couldn't replace everything. You still needed stuff on campus. And the result was something that one of our folks coined the term of cloud sobriety. There was sort of this massive pullback. What short memories we have because it's happening again. For slightly different reasons, there's more cloud providers. They're way more sophisticated. Clouds are designed to handle enterprise needs now, and that is a good reason to use them. Competition has forced a lot of innovation and a lot of cost competitiveness, and there's so much data now that storing it locally is just non-trivial. But they're still promising it that it's somehow cheaper to operate, and it's just not. Right? One of the last trends that Chris did, he said, look, if you're going to the cloud, don't go for a cost play, go for a capability play. And I stand by that. It's 100%. Definitely use the cloud. Just be sure you're using it for the right reasons. All right? The reason really is that, look, at the end of the day, these are for-profit companies, private companies, right, that market themselves as public utilities, and they're not. All right, and that they're possibly the most successful ransom scheme in history. You get your data in, and you have to pay to get it out. You build a bunch of tools using their services, which is going to make it cheaper, and that's the only place you can do that anywhere. If you need to pull it out and do it somewhere else, you got to re-architect it from scratch, right? They're starting to talk about getting rid of the egress fees because people are starting to realize this, but it locks you into using their services, for science, to cloud or not to cloud? That is the question. So can you do real HPC in the cloud? Yes, you can, but it depends on what kind you need, 100%. Can you create a secure environment? Absolutely, but it's totally yours to screw up. All right, there's all sorts of settings. There's a little bit different approach, and the models are different. Can scientists use it out of the box? Absolutely not. Absolutely not. They cannot. It requires a lot of setup of services, user interfaces, platforms. They say, hey, I just got a credit card. I'm going to get in there. And they look at that. They're like, what? I have no idea what to do here, right? Unless they've done it before, unless they're the top 1% of sophisticated users. And even they need to architect their environments, right? And there's some things that are out of the box, and they're good. They're getting better, right? But there are those services. You use those services, you're stuck with them, right? Can we use it for storage? Yep. But, storage in the cloud is equally as complex and hard to price, super hard to price. It's really hard to figure out how much you're going to spend on storage in the cloud, and easy to overdo. And once your data is in the cloud, it costs money to get out. Why use it? Large capacity, automatic upgrades, reliability. If you're using an old machine, turn it off and turn it back on and you'll get a new one, right? That's great. So no life cycles, no hardware life cycles. Virtual orchestration and serverless technologies, these are great, super sophisticated ways of doing things. These things are starting to make their way into local data centers. Containerization and portability of workloads, this is something that happened in all spaces now, but it started in the cloud. Shared standards in architecture, it's a great way to prototype things. If you've got an environment, Everyone's got a user that crashes everything because they're trying something weird, right? And so it's a good way to wall them off and put them there and try new things. And the availability of things like GPUs, that's a great way to get them if you don't want to spend a lot of money on them. So why not all cloud? And this is why I've got cloud set at both red and green. All right, it's both hurting science and it's an innovation. There's a fundamental mismatch between the cloud business model and long-term research. Okay, these are, as I already said that next one, they're for-profit companies. The shortest full scientific study is 5 to 10 years. All right, and some are hundreds of years longitudinal studies. Clouds don't even disclose the time period that they give you if they shut down to get your data back. It's not anywhere. I've read all the terms and conditions. It's not there. I've asked them. They don't answer the question. All right. And the reason is they don't want to talk about it, right? And this should concern you because if you've got 50 petabytes of stuff in the cloud, how long is it going to take you to put 50 petabytes of storage in your data center and get it back? It's going to take over a year easily and toss a whole lot of money. A hybrid computing model preserves data ownership. So, maybe your source of truth is kept locally, so you still own your data, you still hold your data, or at least the primary data. And, you copy data to cloud for analytics and only copy the results back and delete it, right? So you're avoiding egress and long-term cost of storage. The issue, however, is that pure hybrid cloud, despite everyone being promised it for 20 years, is still not happening. All right, and so we're working on that, but it's a whole thing. All right, so I'm going to blaze through this. So trends in networking, you have to move data. If someone tells you that you're going to move your compute to your data, no, sorry, you have to move it at least once. So you have to pay attention to networking. You have to. Enterprise networks are built to be oversubscribed to save money. Of all of your data data generating equipment is at the bottom there, at the very edge, which it is, and it goes through several layers of aggregation and distribution and routing before it even gets to another building in your environment or out to the internet or something like that through firewalls that slow everything down too. You're like 500x oversubscribed by the time you get up there in a lot of organizations, which works fine for web and email and sending documents around, doesn't work well for sending a genome file or terabytes of information. And so this is still, I've used this slide for so long, still the most common high-speed network, okay? Ship it to you. All right, it's high latency, but it works. Right. There's a couple of things I've talked about this for a long time. Science DMZs are perimeter networks that are designed outside of your main enterprise network to be solely for science. They can be designed to be performant. This is something that was invented by the Department of Energy, Energy Sciences Network. They use something like this to connect the national labs. It is a Band-Aid. It is not the solution, right? It works. Even the guy who invented it, Eli Dart, will tell you it is a Band-Aid. We couldn't get people to invest in that. And so it's a sustaining innovation. New models, using things like zero trust and microsegmentation, which actually are kind of aware of where data is coming from and where it's going and routing it over the high-speed parts of the network so that you don't have to scan every packet in the network of your genome files looking for computer viruses. Right, that's not going to work, and then keep all the other data going the way that it normally does. All right, so networking is really key for modern biomedical science. I've said this as long as I've been talking about this. Modern science needs 100 gig data speeds. It just does. Right, if you're still at 10 gig. Especially on your backbone, think about moving that forward, right? At 100 gig, you can transfer a terabyte of data in 1.5 minutes. We're up to 400 gig standards right now. 1 terabit networks are in early release. All right, so let me get through data real quick, and then we're going to turn it over to Laura. So everyone knows what FAIR is, right? Yes? I don't have to go through this? All right. Findable, interoperable, accessible, reusable. How are we doing with FAIR? Any ideas? How are we doing? Pretty terribly, right? It's not going well. It's not great. There's limited pockets of excellence. So why can't we get there? Because, man, we like to talk about it everywhere. We really talk about it. So this is red. This is blocking us. This is really, really not good. The short answer is that it's people. People are blocking this from working, not necessarily technology. The long answer is it's super complicated. It's really hard to do. It's extremely complex. There's lots of historical data, but it could be done if people were motivated to do it, but they are not. That's the problem, all right? There's a lack of unified data standards in the field. There's a lack of sophistication, lack of tools and training, lack of accessibility of solutions, one of our grand challenges. And there's really not a lot of incentive to make the effort. All incentives are individual, like, for instance, NIH grants. Still individual. So the more differentiating you are when you're applying for a grant, the more likely you are to get it, which says, I've got a novel metadata schema. Great. That's going to help everyone. But everyone's like, yes, let's do that, right? And they get that funding. So this has to be a community effort, and there's not a lot of incentive to be community around this, right? And it pays to do your own thing. So, I sort of talked through this. There's lack of unified standards. It's kind of all over the place. There are standards, right? There's standards organizations, right? It's just limited to particular areas and domains of the science, right? I'd say that genomics is probably one of the furthest along on this. I think 3D structures of proteins are also pretty far along, but the rest is kind of all over the place. And these were done because if they didn't, it was going to be a disaster, okay? And so that's one of the problems there. So people try to solve it with data platforms. They're everywhere, right? It's another buzz-loaded space. We've got data lakes, data oceans, data fogs, swamps, islands, universes, warehouses, commons, ecosystems, meshes, fabrics, data X, right? Name it something, that's your latest thing, right? Everyone's all into data meshes now. Why? Because we're trying to fix interoperability. The truth is that none of them are designed to be interoperable. They're just not. There are silos of excellence when they work well, right? And they are not accessible to long tail of science. Most of them are API-driven or Jupyter Notebook-driven. Sorry, a really smart laboratory scientist is not going to have a clue what to do with a Jupyter Notebook, so that's not going to work. And so you need a diversity of tools and approaches, and they're not really cross-compatible. And then I mentioned this earlier, and so this whole trend is red. We don't understand the value of data in our space. We don't understand it, okay? And this is key to make a difference here. So in general, there's two different ways to look at it. There's the actual cost of data, the investment, the monetary investment, how much it costs. How many of you purchase data sets out there for use internally? Quite a lot, I think, in pharmas mostly, right? And then there's understanding the scientific data value. Should we keep this file? We've been debating this for 20 years. We still keep it all, right? Will this data ever be reused? How long do we keep it? What's the impact of that? And without that understanding, everything is high value, so we keep everything. That is also known as hoarding, okay? And so, we have to infinitely expand storage. We can't do it. We can't prioritize that. And, FAIR also, just as another zinger out there, doesn't contemplate data quality, and that's something we also need to look at. All right, AI. I only have a few slides left, so I'm going to get through this. So, as I said earlier, the hype is increasingly ridiculous, but why are we interested? We're interested because we transitioned from the information to the analytics age to gain value from our collected data. We collected a crap load of data, it was all backed up, and we're like, oh crap, how do we even go through this? AI is going to do it for us. No. And so that brings me to the AI slide, because, no talk's complete without an AI slide. Please say AI one more time. Let's all jump off the bridge together. Look, let's be honest. It's a remarkable but very overhyped thing. It's reminiscent of big data. Most people don't really understand what AI/ML is, and to steal from David's talk this morning, most people think it's this. Most people think that it's just going to be scary and horrible, and they're going to destroy us, right? But it's not, right? And every organization, every person tells me that they need to be AI ready. No, all right? Who looks at Gartner hype cycles? So this is the one from 2023. Notice how much is on the innovation trigger side of things, on the far, far left. And also look at how much is on the peak of inflated expectations. It's a lot, right? And then there's a few things that are falling down in the trough of disillusionment, and then a few things that are on the slope of enlightenment. Nothing is in productivity. Not a thing. Not one. All right? This is where we are at. AI is research, important research. It is good. It is good research. It is not something that we should 100% rely on for things, because it is still research, all right? In life sciences, we're about 2 to 5 years away from productivity on things. There's some things that are real close, like, pathology identification, all right? That's a well-quantified field, and that is actually making a lot of difference. Robotic-assisted surgery, things like that are really, really good. But the problem is that this is kind of a bad graphic of all the different parts of artificial intelligence, right? The problem is that when people are talking about AI, most are talking about that and only that right now, And they think that's all it is, but there's all this other stuff. Now with LLMs and GPTs and things like that, it mixes a couple of these things, but most people are just thinking of that. So, what's driving the AI hype? Anyone know? What's driving it? That's what's driving it. Okay. Our friends in green, NVIDIA, right? I like them. They're doing really, really great stuff. But Intel and AMD were right behind them. This was a massive marketing scheme that was launched about 7 or 8 years ago, where NVIDIA became the AI company. And it's really, and they've done massive good for AI, for real. They've got lots of libraries. They've got lots of tools. It's really great. But they're also driving the hype to a fever pitch. And marketing is very, very convincing because a lot of people don't really understand it. All right, last slide. So trends recovery. This is sort of like, okay, let's take a deep breath. We just blasted you with stuff. So what's the thing? AI, and also AI. Okay, there's a lot of it out there. So let's pull back. Let's be a little more realistic about AI. Let's use it effectively and responsibly, not, sociopathic toddlers. All right. There's still a big push for a cloud. On the top 500 list, the fastest supercomputers in the world in November, Microsoft Azure was number 3 at half an exaflop. Right, that's really interesting. The cloud push is slowing down. On-premises planning is coming back. GPUs again. We've had the same data problem for 15 years. They all just got bigger and more complex. So more storage for AI, and new silos that pop up that make a difference locally. The meta pull out from all this is that IT is still disconnected from the science mission. It's getting better. There are research computing folks out there. I've been talking about this for 13 years. And, look, we kind of build a business off of it, so great, except that I'd like to fix that and move on to something else. And so science is disconnected from supporting infrastructure, and they aren't incentivized to change. And data science is caught in the middle, being a bottleneck, right? We are on the verge of making meaningful change because of and in spite of AI/ML. And let me just explain that real quick. The reason is that in order to do some of these machine learning algorithms, you have to have well-categorized, well-understood data. Right? You have to. And so people are like, we need our data to be AI ready. Awesome, let's do that. But let's actually just make it analysis ready, okay, for all analytics, because it's going to work for all the things. And now we're not just doing AI. So, all right, thanks for listening. I'm going to turn it over to Laura, and we'll take questions afterwards.
Thank you for listening to Bio-IT World's Trends from the Trenches podcast.